Good, so let's start. I hope everyone is okay. There's a question on division, so let's have a recap of division of complex numbers. And as I said last time, for you to be able to divide complex numbers, you must understand what's an absolute value of a complex number. And you must also be able to know what's a complex conjugate. Complex conjugate. So just like rational conjugate rationalizes an irrational number, complex conjugate will make a complex number a real number. The complex number has a real part and imaginary part. So when you multiply a complex number by its complex conjugate, the imaginary part disappears and you get the real part. So given any complex number, let's say z is a plus ib, we define the absolute value, which we denote by these two bars as the square root of the square of the real part, sum the square of the imaginary part. So the real part is a, the imaginary part is b. So when you square these guys and add them, find the square root, this is the absolute value for your complex number. And then the complex conjugate, given any complex number, a plus ib, complex conjugate denoted by z bar, simply a minus ib. So to get complex conjugate, simply change the sign of the imaginary part. So instead of a plus ib, I have a minus ib. And I gave you some axioms that if you multiply a number by its complex conjugate, you always get the absolute value squared, or in this case, a squared plus b squared. This is all we need to know for us to be able to divide the complex numbers. And of course, you need to know how to multiply complex numbers. So I will give an example. I think the best way is to give an example. For example, let's say we want to...
Excuse. Sir, please, may you repeat for the absolute value, please?
What about the absolute value?
Please, can you repeat the formula? How you got it? The formula.
How I got this formula?
Yeah.
This is the definition. This is not a formula. This is the definition. In mathematics, definitions, you take them the way they are. So this is how we define the absolute value of a complex number. Given any complex number with the real part and imaginary part, to compute the absolute value of the complex number, take the real part, square it, take the imaginary part, square it, add them, and then find the square root. It's a definition. It's not. This is not derived. This is how it is defined. Just the way we define the complex number as a number with a real part and an imaginary part. But as we shall see in representation of complex numbers, I hinted that the absolute value of a complex number has some geometric meaning. There's a geometric meaning to the absolute value of a complex number.
Okay, sir, thank you.
I don't know if I got your question right, Abdiakim.
Yes, sir, thank you.
Yeah, it's not a formula. This is how it is defined. Okay. So let's take an example. Maybe a simple example, 2 4 I, you want to divide this by 1 plus I. You want to divide these two numbers, okay? 2 plus 4I divided by 1 plus I. So the first step is to find the complex conjugate of the denominator. In this case, the denominator or the divisor is 1 plus I. So you need complex conjugate of 1 plus I. What's the complex conjugate of 1 plus I?
1 minus I.
Good, that's 1 minus I. Simply change the sign of the imaginary part. And then the next step is to multiply both the numerator and the denominator by this complex conjugate. That's step 1. Step 2, we will take 2 plus 4i divided by 1 plus I. We multiply the numerator by 1 minus I and multiply the numerator by 1 minus I. So remember, I'm not changing the meaning of this expression because 1 minus I can still cancel out and I get back to what I have. So I'm not changing the meaning of the expression, okay? Then now the last step is to just simplify, do the multiplication, okay? So in the numerator we want to take all the terms on the left-hand side, multiply by all terms on the right-hand side. So we take 2 multiplied by 1 minus I plus 4i multiplied by 1 minus I. All of this divided by, so down here, we'll use this definition that a complex number multiplied by its complex conjugate gives you the absolute value squared, okay? Because 1 plus I is the complex conjugate of 1 minus I and vice versa. So that means if you multiply 1 plus I by 1 minus I, what you should get is 1 squared plus 1 squared. So here if I had ZA plus IB, I just get A squared plus B squared. That's why here I have 1 squared plus 1 squared. So in the numerator, you get 2 times 1 is 2 minus 2i, I'm just opening the bracket, plus 4i, and then plus 4. All of that divided by 2, where 2 is 1 squared plus 1 squared. 1 squared is 1, of course, by 2, that's just 2. And here I'm getting a positive 4 because I have, this is 4i times negative I. So when you take 4, negative 4, but then there's an I times minus I, it gives you a negative 1. So the negative times negative, you get a positive. And then at this stage, just combine imaginary parts together and combine the real parts. So the real part, there will be 2 plus 4, which is 6. It's 2 plus 4. And then the part will be minus 2i plus 4i, which is plus 2.
Excuse me.
And you get your final answer as 3 plus I.
Excuse me.
Yes, please.
I got lost where you said that the conjugate, when you multiply the absolute value squared, it became 2 because it's 1 plus I.
No, 1 plus 1. This is 1 plus 1.
So you don't count the I.
No,
You don't do the I squared.
I squared where? Here.
You see here, step 2.
Step 2.
The denominator.
Mm-hmm.
It's 1 plus I
Times 1 minus
brackets. Yeah.
Yes.
Oh, okay.
What I'm doing, I'm using this formula to save myself all this work. I could as well go ahead and expand this.
I got you. Thank you.
For example, what I did there is just 1 plus I times 1 minus I. Instead of going through the pain of expanding this, I know this is the complex conjugate of this. When I multiply, it should give me the absolute value squared. But I could just take 1 times 1 minus I plus I times 1 minus I. So this is 1 minus I plus 1. There's a positive because this is negative I, but then I times I is I squared. So negative, negative, this becomes positive. You have minus I and plus I. That's of course 0. So 1 plus 1 gives you 2. And that is the 2 that we have here.
Thank you.
So I'm using this definition to simplify so that I don't have to multiply out what is in the denominator. Okay? Any question?
Yes.
Go ahead.
At the denominator, can I still use the difference of squares instead of the...
Good. You can use the difference of squares. You can use the difference of squares. That's a very good observation. Excellent. You can use the difference of squares, but you must remember that I squared is -1. Okay, so we have 1 plus I multiplied by 1 minus I. By difference of squares, okay, so remember difference of squares, if you have A plus B times A minus B, this should give you A squared minus B squared. So in this case, A is 1, B is I, so I should have 1 squared minus I squared, okay? But what is I squared? I squared is -1. So this gives you 1 minus -1, which is 2. Okay?
Excuse me, sir.
Yes.
I log in a bit late. Could you go over?
You logged in late,
Yeah, you go over.
and you know you're supposed to be punctual. So what should we go over?
From the beginning?
From the beginning.
Yeah.
And that means we'll stop 10 minutes past time. Huh?
No problem with my connection, my internet.
Okay, so someone asked about division of complex numbers. In the last class, we did addition, subtraction, multiplication, and division. And before we started the class, someone asked that we repeat how we divide complex numbers. And I've said that for you to divide two complex numbers, you must know how to find absolute value of a complex number. You must know how to find complex conjugate of a complex number. And lastly, you must know how to multiply complex numbers. All these three items are required for you to be able to divide two complex numbers. Okay, so given any complex number, Z with the real part A and the imaginary part B. So I said the imaginary part is simply a coefficient of I. Good. The definition of the absolute value is that if Z is A plus IB, then the absolute value is simply the square root of these real and imaginary parts squared, and you sum them. This is how you compute the absolute value. And as you shall see in the representation, the absolute value actually represents the length of the vector of the magnitude. And then the complex conjugate, to find the complex conjugate of a complex number, simply change the sign of the imaginary part. So if you have A plus IB, complex conjugate of that is A minus IB. And lastly, we gave this axiom that if you multiply a complex number by its complex conjugate, this gives you the absolute value squared. This formula will help us to simplify multiplication in the denominator. So once I know this formula down here, I don't have to multiply what is in the denominator. Because I know I'm multiplying a number by its complex conjugate. So straight away, just square the real and imaginary parts and then add them to get what is in the denominator. So your only worry should be how to multiply the complex numbers which will be in the numerator. For example, 2 plus 4i divided by 1 plus I. Simplify this or express the form A plus IB. The first step is to compute the complex conjugate of the denominator. In this case, the denominator is 1 plus I. Complex conjugate, simply change the sign. So from plus to minus, so we have 1 minus I as the complex conjugate of 1 plus I. That is step number 1. Step number 2, use these complex conjugates to multiply both the numerator and the denominator. So we have taken 2 plus 4i divided by 1 plus I, and we multiplied the numerator and the denominator by the same complex conjugate. And I stated that this does not change the meaning of the expression because it's like you're multiplying it by 1, and you know 1 is a multiplicative identity, because you could still go ahead and cancel these terms and get back to what you had before. Now the last step is to simplify this. Open these brackets, multiply out terms, and of course, keep in mind that I squared will always give you -1 because we define I as the square root of -1. So I've taken all the terms on the left-hand side and I used to multiply all the terms on the right-hand side. So I have 2 multiplied by 1 minus I plus 4i by 1 minus I. And then in the denominator, I'm having a number and its complex conjugate. So straight away, or using the difference of squares as we've done here, you will get, or using this definition, A and B are both 1. So 1 squared plus 1 squared gives me 2. So you should only be worried about what is in the numerator. And opening this bracket, 2 times 1 is 2. 2 times minus I is minus 2i. 4i times 1 is 4i. And then 4i times negative I is positive 4. We are getting a positive number because I squared is negative 1. So you'll have here 1 minus minus 1. 1 minus minus 1 times 4, which gives you positive 4. And then the last stage is to combine the real parts and the imaginary parts. So the real part of this denominator is 2 and 4. 2 plus 4 gives me 6. Imaginary parts are minus 2i and 4i. When I combine this, I get a 2i. And the denominator is a 2. So 6 plus 2i divided by 2 gives you 3 plus I. There's another method I gave you, which you can still use to do division, but you are required to know how to solve simultaneous equations. So let us try to approach this same problem, but now using the other method. And the argument is this. The argument is that we expect that when you divide two complex numbers, we will get another complex number. So straight away, let 2 plus 4i divided by 1 plus I, let this be x plus iy. It will be another complex number. So x is a real number, y is a real number. So this will be a complex number. Then now what you do, we do multiplication. To do away with the fraction on the left-hand side, multiply all terms by 1 plus I. So multiply this side also by 1 plus I. Over here, 1 plus I and 1 plus I cancel out, and you get 2 plus 4i is equal to, now this end we need to multiply, okay? So we have x into 1 plus I plus iy into 1 plus I. So this gives me x plus xi plus y times I. And then there's an iy times I. What do we have here? What's the last term here?
Y I squared
And what is I squared?
minus 1.
Good. So this is going to be minus y. So on the left-hand side, we have 2 plus 4i. On the right-hand side, let me combine real parts. So the real parts here are the ones that do not have the I, it's x minus y, plus the imaginary parts are the ones that have the i's. So in this case, xi. Okay. Then now, two complex numbers will be equal if and only if the real parts are the same and the imaginary parts are also identical. So from this stage, take the real part of the left-hand side equates to the real part of the right-hand side. And take the imaginary part of the left-hand side equate to imaginary part of the right-hand side. So the real part of this side is 2. What is the real part of the other side, the right-hand side?
X minus y.
X minus y. Similarly, the imaginary part of this side is 4. Imaginary part of this side is x plus y. So you have two simultaneous equations with x and y. You need to solve for x and y. I know we have not done simultaneous equations, but this is a very easy system to solve. First, you could add the equations. So 2 plus 4 is 6 to give you 2x. Therefore, x is 3. Then once you have x is 3, you can use any of these equations to find the value of y. For example, in the second equation, 4 is 3 plus y. Therefore, y is equal to 1. So initially I had let the fraction to be x plus iy. But now this x we found as 3. The y we
The board can't be seen.
1.
We can't see your handwriting.
Yeah, maybe try taking the camera away from the board a little bit.
I cannot see. Oh, okay, okay. Is that better now? Is that better now?
No, it's still blurry.
No, it's not.
Yeah, so I was explaining how to solve these two simultaneous equations. I know we have not done simultaneous equations, but this is just an alternative method to divide complex numbers. You let it be some given complex number, because you know when you divide two complex numbers, you expect another complex number. This happens because the complex numbers form what you call a field. So divide any two complex numbers, you expect a complex number. That's why I let this be some complex number of real part is an unknown value x, imaginary part is some unknown value y. And then by the property of complex numbers, that two complex numbers are only equal if the real parts are identical and the imaginary parts are also identical. So with that, I come up with two simultaneous equations whose solutions are 3 and 1, which gives you 3 plus I, just as we had with the other method, how to divide complex numbers. Question? Any question on either of these methods?
How did the answer get to 3 plus I?
From here,
Yeah,
or from here,
from the other side.
this other side.
Yeah.
Good. So this other side, you have 6 plus 2I divided by 2, which is the same as 6 divided by 2 plus 2I divided by 2. 6 divided by 2 is 1. So I have 3 plus I. Okay.
Yes.
Yeah.
Good. Let's look at something else, unless there's a question.
Sir,
Yes,
sir, please repeat for powers.
powers.
Yeah.
We haven't done powers. We have not done powers. We have to do powers and roots. Huh?
Okay.
Okay, so first of all, let us look at representation. Representation of complex numbers. Complex numbers. Recall, I know you have seen what we call Cartesian plane, huh? Horizontal x-axis and some vertical y-axis. So if there is some point here, let's say A, let's say this is 2, this is 4, let's say there's another point here, B, maybe this is -3, this is 4, then you can refer to this point as 2, 4, where 2 is the x coordinate, 4 is the y coordinate. And you can refer to the point B as
Excuse me.
-4, where -3,
Me?
the x coordinate, and 4.
Excuse me.
Yes?
It's blurry. It's blurry. Again.
Oh. Is it the pen? Is it the pen I'm using, or let me try use another pen? How about if I use a black pen?
Yeah. Let's see.
Black pen should be better.
Yeah.
Yes, I was just reminding Cartesian plane. Have you met a Cartesian plane before? Where you have the real axis on the horizontal and the y-axis, also a real axis on the vertical. And you can locate points depending on you can locate points using coordinates pairwise. So example, if I give you a point A there, this is 2, maybe this is 3, another point B, this is -1, or maybe this is -2, and this is 4, and here is 5, this is 2. So this is have A, B, this is B, B is already up, D. So that we can locate any point on this plane. This is called a Cartesian plane. It's simply Cartesian product. You remember Cartesian product of sets? We defined A cross B as the set AB, where A comes from A and B comes from B. For example, if you have two sets, let's say maybe 2, 6. The Cartesian product of this set is going to be 1, 2, and then 1, 6, and then 2, 2, and 2, 6. And then each of these elements of this set is a coordinate. You can use it to locate points. Okay. So this is what the Cartesian plane does. The Cartesian plane is simply R2, which means you take the real line cross product with the real line, where the definition of cross product is as given here. So the first coordinate will come with the real number. Second coordinate is also a real number, just like in this diagram. So the first, all the x coordinates are on the horizontal axis, y coordinates are on the vertical axis, and this is usually called the xy plane. So the point A will have coordinates 2, 3. The point B will have coordinates -1, 3. So -1 is the x coordinate, 3 is the y coordinate. The point C will have -2, 4, -4. And then the point D will have 2, -5. So the 0 at the origin. This is how you represent coordinates in the Cartesian plane. Now we define complex number as a number of the form A plus IB, where A and B are real numbers. A and B both belong to R. So it means you need two real numbers to define a complex number. Therefore, you can just say Z is simply A, B, where A and B belong to the real line. And the first coordinate is the real part of the complex number. Second coordinate is the imaginary part of the complex number. So if you have a pure imaginary number, for example, if you have, let's say Z is IB, which is pure imaginary, so meaning the real part is 0, in coordinate form, this will be 0, B. If you have a pure real number, like let's say 5, which means the imaginary part is 0, so this should be 5, 0. We can use this same analogy to define what we call a Gantt diagram. So just like in the Cartesian plane, it's still a matter of taking cross product, but now we have, this is called real axis. This is called imaginary axis. Imaginary axis. I've just changed the names of the axes, but what we do is the same. So let's say I have a point K. This is A. This is B. So my complex number is Z, is A plus IB. The real part of this complex number is A. So as you can see on the horizontal axis, I have real numbers. And then on the vertical axis, we have imaginary numbers. So after 1, you'll have some I there. And this is normally called Argand diagram. Argand diagram. This is how we represent complex numbers in the rectangular coordinate system. So your coordinate system where you have the real numbers on the horizontal axis and the imaginary numbers on the vertical axis. Actually, its initial definition was that the square root of -1 is simply a rotation through 90 degrees. So if you start to measure from the x-axis 0, you notice that this angle is 90 degrees. So its definition of a complex I, we get the definition of I as square root of -1. John Argand defined I as a rotation of the real axis through 90 degrees. So if you rotate this real axis through 90 degrees, you'll find yourself on the imaginary axis. So what happens here is that if you have a number, let's say, let me give you examples of how to represent numbers on this Argand diagram. So let's say we have 3 plus 6i. Let's say I have 2 minus 7i, minus 1 minus 6i, 0, 1, pi. We want to represent all these numbers on this Argand diagram. So I will calibrate my scale. So this is 0, 2, 4, 6, 8. This is -2, -4, -6. This is -2, -4, -6, -8, 2, 4, 6, 8. So the first one is 3 plus 6i. The first coordinate, the first real part is 3, will lie on the real axis. The imaginary part will lie on the imaginary axis. So if I'm looking for 3, 6, this should be represented by the point 3, 6. So on the real axis, locate the point 3, and then move vertically upwards. This is the point. So this is going to be 3, 6. This will correspond to the complex number 3 plus 6i. 2 minus 7i. Locate 2 on the real axis. So this is 2. And then minus 7i on the imaginary axis is down. So go down like that, somewhere there. This is 2, minus 7, which will represent the complex number 2 minus 7i. So what I'm trying to say is that each and every point on this Argand diagram, or each and every point on this z-plane, it's also called the z-plane. Every point here corresponds to a single complex number. So for example, the complex number 3 plus 6i will correspond to the point 3, 6. The one at the origin, the complex number 0, will correspond to the coordinate 0, 0. So if I was to represent 0, I'll just represent it by a dot at the origin, because I stay at the origin and I don't move anywhere along the real axis or along the imaginary axis. You stay at the origin. -1, -6, locate -1 on the real axis. So this is -1, and then -6 somewhere there. So this is the point -1, -6, and it will correspond to the complex number -1, -6i. In general, to represent a complex number in the Argand diagram or the z-plane, take the first coordinate as the real part of the complex number, and take the second coordinate as the imaginary part of the complex number. So if I give you a complex number, let's say x plus iy, then the real part will be on the real axis, will be the first coordinate. The imaginary part will be on the imaginary axis. That will be a second coordinate. Okay. There's another way to represent complex numbers. Called trigonometric or polar form. Is there any question about the Argand diagram? You only need to remember that every point on this plane corresponds to a complex number. And similarly, every complex number can be located on this complex plane by taking the real part to be the coordinate on the real axis, imaginary part of the coordinate on the imaginary axis. Is everyone okay with the Argand diagram of the Z plane?
Yes.
Okay. Let us look at trigonometric form. First of all, let me remind you of some few definitions. If you have a right angled triangle, let's say this is theta, this is x, this is y, this is r. So we have a right angled triangle. It's an angle theta. The length of this side is x, the length of this side is y, the length of this side is r. Could someone define for me sine of theta, cosine of theta, tangent of theta from this triangle? Have you done
Sine theta?
ratios before?
Yes.
Good. So what is sine of theta?
Y over R.
Y over R.
Sine theta?
Y over R.
Y over R.
Cosine of theta?
X over
X
R.
over R.
Good. X over r. How about tangent of theta?
Y over X.
Y over x. Is everyone okay with this? Have you all done trigonometric ratios? I don't want to assume. Huh?
I can't remember. It's been years. So
Been years, good. So if it's been years, there is this Sokatoa. Don't know whether you met this before. So first, this tells you that sine is opposite divided by hypotenuse, SO. So if you have an angle theta, opposite is the length of the side directly opposite, as the name suggests, and then the hypotenuse is the longest side. So if I'm looking for sine, SO, S is O divided by H. So opposite here, the length is Y, hypotenuse is R. Then the second part, CAH, stands for cosine is given by the length of the adjacent side divided by the length of the hypotenuse. So cosine of theta, I need the length of the side adjacent to theta, which is x divided by the length of hypotenuse, which is r. So that's why I have x divided by r. And then tangent is the length of the opposite side divided by the length of the adjacent side. So tangent of theta, the side opposite theta is y, as length y, and the side adjacent theta as length x. So that's why we have tan theta is y divided by x. So for those of you who have forgotten, you might just want to remind yourself of this Sokatoa. It will help you to sort of memorize the definitions of these trigonometric ratios. Okay. Now, from the Argand diagram, suppose I have a point somewhere there, some point, let me call it Q. Let me call this point Q. This point Q is Z plus Z given by X plus IY, where X is the real part, Y is the usual imaginary part. So that means from the origin, I need to move X units along the real axis. This is real axis. This is the real part of Z, the imaginary part of Z. And then we have Y units up. And therefore, we can come up with this triangle. can come up with this triangle. Let us call this angle theta. So instead of in the rectangular coordinate, representing the point Z as x, y, where x is the real part, y is the imaginary part, I want to use the definitions from these trigonometric ratios to use simply theta and r. So this is my x, this is y, this is r. From this first ratio, r sine theta is y divided by r. This means if I multiply both sides by r, that y is r times sine of theta. From this first ratio, I've just multiplied both sides by r. So r times sine theta is r sine theta. Y over r times r is simply y. Secondly, here we have that x is r times cosine of theta. Okay. From these two definitions, I know y is r sine theta, x is r cosine theta. We have defined z as x plus iy. But we know that x is r cos theta, y is r sine theta. So let me come and replace them. So here I have the same z is the same as r times cosine of theta plus I times r sine of theta. R is common, you can factorize. We have done factorization before. So you can write z as r into cosine of theta plus I times sine of theta. So all I need to know is the value of r and the value of theta, because sine and cosine, I know the definitions. Therefore, I can still represent the point Q using a different coordinate system. I need r, which is this length, it's just the magnitude, or if we are considering this as a vector. And then theta is simply the angle that you will move from the horizontal axis upwards. So remember, we measure angles on the Cartesian plane or the Argand plane, and the clockwise is positive. So this is positive. If it was going clockwise, it would be negative. So instead of representing the point Q as x, y, in this case, I will represent Q as r, theta, where r is the length of the hypotenuse of this triangle, and theta is this angle above the angle you move from the horizontal x-axis upwards. So we need to know how to compute r and theta given x and y, and also how to compute x and y given r and theta. These two formulas will help you to move from rectangular system to trigonometric system back and forth. Let me give you an example. But before the example, I also need to remind you of Pythagoras theorem. Given this right angle triangle, we know that x squared plus y squared is r squared. Pythagoras theorem on this triangle, this is Pythagoras theorem. The square of the base plus the square of the height is the square of the hypotenuse. From this, I can find square root on both sides. So square root of x squared plus y squared is going to give you r. Have you seen this such a definition before? Square root of x squared plus y squared.
Yes.
What does it represent? If you're dealing with the number z is x plus iy, what does square root of x squared plus y squared represent?
Absolute.
Good, absolute value.
Absolute value.
Same as the absolute value. That's why I tell you the absolute value will have a geometric meaning. So the meaning is simply the length of the vector from the origin to the point that you are representing on the complex plane. And then to find the angle theta, you can use any of these ratios. If you know sine theta is y divided by r, suppose I give you y divided by r, to find theta, just compute the sine inverse. If I give you x and r, to find theta, use cosine inverse. If I give you x and y, to find theta, use the tangent inverse. So any of these ratios can give you the angle. So theta will be given by the tan inverse of y divided by x. Or some books will call this arctan y divided by x. So with these two, we can move from rectangular representation to polar representation and back. Let me give you an example. Example. Find rectangular representation. Representation of the complex number 6 times cosine of 30 plus I times the sine of 30. So in this case, R is 6, theta is 30. If you are to represent this in a diagram, you know that the angle is 30. So this angle here would be 30 degrees, and this length is 6. So it is this point. You're looking for the coordinates of this point. Of course, in polar form, I just need 6, 30 to represent this. But in rectangular, I will need to compute x and y. We know that x is given by r cos theta, and y is given by r sin theta from the definitions I gave you. Just substitute in this formula. X will be 6 times cosine of 30. What is cosine of 30?
0.5.
Y should be 6 times sine of 30. I think the sine of 30 that is 0.5. So sine 30, so this should give you 3. Cosine of 30 should be 0.866, which is the same as square root of 3 divided by 2. So this is the same as 6 times square root of 3 divided by 2, which is the same as 3 root 3. So in other words, this is simply the complex number 3 root 3 plus 3 I. So the x coordinate here will be 3 root 3, y coordinate here will be 3. How about the other way around? Suppose I give you a number in rectangular system and I want you to represent it in the polar system. Let's take a simple one. Represent 1 plus 3i in polar system. Polar coordinates. Okay. So in this case, the real part is 1, the imaginary part is 3. So here x is 1, y is 3. We define r as absolute value of z. So in this case, absolute value will be the square root of 1 squared plus 3 squared for this complex number, which is simply square root of 10. 1 squared is 1, 3 squared is 9. So 9 plus 1 gives you 10. So the radius should be square root of 10. How about the angle? You could use any formula. So I choose tan. So I want to find arctan of 3 divided by 1. Because 3 is y, so y divided by x, 3 divided by 1. What's arctan of 3? What's the tan inverse of 3? Those who have a calculator, you can compute that.
$21.5657.
21.
71.
1.56.
57.
So therefore, so the same number 1 plus 3i can be represented using just these two coordinates, root of 10, 71.5 degrees, meaning that you will need to move a distance of root 10. So if this is your Argand diagram, the length of this vector is going to be square root of 10, and then this angle is going to be 1.56 degrees. And this is the complex number that you are interested in. There is one more way to represent complex numbers, and we will need a formula called Euler's formula. Euler's formula. So with Euler's formula, from this trigonometric form, we can represent complex numbers in what we call exponential form. But first of all, let's see what Euler's formula says. Euler's formula says that the exponent of I to the theta is the same as the cosine of theta plus I sine of theta. Those of you who have done calculus, we normally, the way to derive this formula is to write exponent I theta as Maclaurin series around the point x I theta. And then you will find that after doing your expansion, you will get two infinite series. The infinite series, Maclaurin series for cosine of theta, and the Maclaurin series for the sine of theta. So take this as a definition, that exponent I theta is cosine of theta plus I sine theta, where E is this irrational number which starts by 2.718 and goes on forever. It's an irrational number. Some people call it the natural base for logarithms on the Napierian. Okay. We just saw that if we have a complex number z is x plus iy in the rectangular system where x is the real part, x becomes the first coordinate, y is the imaginary part, becomes the second coordinate. We just saw that we could also do this as r cosine of theta plus I times r sine of theta, where r cosine of theta is x, r sine of theta is y. And by factorization, you can write this as r into cosine of theta plus I sine of theta. At this stage, this is the Euler's formula. So instead of cosine of theta plus I sine of theta, this part can be written as exponent I theta. So you can write this part as r times the exponent of I theta, because I've invoked Euler's formula. So these are three ways to represent complex numbers. You can represent complex numbers in rectangular coordinates, where the first coordinate on the horizontal axis is the real part, coordinate on the imaginary axis is the imaginary part. That's number one. Number two, you can represent complex numbers in polar form, where you simply need the absolute value of this complex number will be the radius, which is simply the distance that you will cover from the origin up to this point that corresponds to this complex number. And then theta is the angle that you take from the positive horizontal axis. So in this case, you're moving in the anti-clockwise direction for it to be positive. And then thirdly, you can have the exponential form where you need to invoke Euler's formula. So you can write a complex number as r exponent I theta. All these three different forms. So the first one is this rectangular, then there is this polar form, and then there is this exponential form. They refer to the same. There are different ways of writing the same complex number. And as we shall see in finding the powers and the roots, so some forms will be preferable to use. For example, when finding powers or roots, it's more easier to use the exponential form or the polar form as opposed to the rectangular form. if you want to find powers and roots of complex numbers in a more easier way, it's advisable that you use the exponential form or the polar form instead of the rectangular form. Okay. Questions before I proceed? Are there questions?
Yeah, how would you present like such like this in an exam?
Good. Possible questions in an exam? So many. I could ask you, for example, I could ask you to express maybe 2 minus 6i in polar form or polar coordinates. I could ask you to graph 7 plus 20i in the Argand diagram. Argand plane. These are possible questions. I could also ask you to express maybe 2 exponent, I don't know, I pi over 4 in rectangular form. Okay. These are possible questions from these 3 representations. So you should know how to move from one representation to the other, because depending on what you want to do with these complex numbers, either of those 3 forms may be preferable to the others. And I've just hinted that when finding roots and powers of complex numbers, it's easier to use the exponential form and the polar form as compared to the rectangular form. For example, if I ask you to find, let's say 2 minus 6i raised to power 100. We have not done binomial expansion, yes, but it's very hectic to compute the 100th power of this number as it is in the rectangular form. But if I write it in exponential form like this, I'll use what we call De Moivre's theorem, which I'm about to give you, and I will solve this in 2 steps instead of having.
Excuse me.
Instead of having to deal with 100 terms, I will now deal with just 2 terms.
Excuse me. What
Yes.
have you written on the third one? I can see 2e what?
E to
The
the
power
pi
of
over 4.
how?
2 exponent I to the pi divided by 4. Pi. Of course, here the angle is in radians. You can express angles in degrees or in radians. I hope you guys know how to move back and forth. You know that 2 pi radians is the same as 360 degrees. So angles can be given in radians or in degrees, depending on whatever you're doing. More questions? Okay, let us see how to use De Moivre's theorem to compute powers of complex numbers. You guys should ask a lot of questions. Huh? Don't suffer in silence. Ask questions. Powers of complex numbers. Complex numbers. So in the rectangular form, we are representing a number z as x plus iy, where x is the real part, y is the imaginary part. Okay. In the polar form, we could write this as r times cosine of theta plus I sine of theta, which you can also write in the exponential form as r exponent of I the theta. Okay. Now the Mover's theorem tells you that if you have a number z and you raise it to the power n, then this is the same as taking the r raised to n and then the cosine of n theta plus I times the sine of n theta. This is called the Mover's theorem. De Moivre. RE. De Moivre's theorem.
They do. They.
De Moivre is a French guy. So in French, OI is moi. It's Abraham de Moivre. He was a French guy who stayed in England. So he did this theorem when he was in England, where he met people like Isaac Newton and Manali and the rest.
So I have a question.
Yes.
So before the sign is there an I.
Before what?
The sign is there an
Yes,
I.
there's an I. There is an I. So for example, let me start with the numbers which are already in polar form, okay? Compute the powers of the following numbers. Powers of the following numbers. So let's say part A, we have 2, maybe exponent I pi over 4. Maybe part B, you have 2 times cosine of 20 degrees plus I sine of
And see.
degrees.
So blurry. Right.
My pen is blurry.
Like when you've written A2 raised to E, we can't see that. Like it's so small.
It's so small. Let me.
Yeah, like the first example too.
How about this side?
Okay, that's better.
Good. So I'll use this side. Let's say I want to compute. Let me call this Z. Let me call this K. So part A Roman 1. This is Z. I want to compute Z squared. So in this case, n is 2. Remember here, n is an integer. N belongs to Z. So the theorem says that if I want to compute Z to the n, then find the n power of R and then multiply the arguments, multiply the angle by n. So in this case, Z squared should be the same as 2 exponent I pi divided by 4, all of this squared, which should give you, by Euler's formula, what you have inside should be 2 times cosine of pi by 4 plus I times the sine of pi by 4. You are raising everything to 2. But the theorem tells you that take the R and raise it to n. In this case, R is 2. So I take 2 squared. And then inside the bracket, multiply the angle by n. For our case, n is 2. So I'll multiply this angle by 2. So this should be times cosine of 2 times pi divided by 4 plus I times sine of 2 times pi divided by 4. 2 squared, 4. Pi, 2 pi by 4 is the same as cosine of pi by 2 plus I sine of pi by 2. And of course, this in the rectangular system, remember pi by 2 is 90 because we know 2 pi is 360, therefore pi is 180, so pi by 2 is 90 degrees. Cosine of 90 degrees is 0. Sine of 90 degrees is 1. So this number is going to be the same as 4i. Give your answer in the rectangular form. It's going to be 4i. Because the first part is 0. Cosine of 90 is 0 and sine of 90 is 1. So it's going to be 4i.
Excuse me,
Yes?
I have not understood.
You've not understood?
Yeah.
Good. We'll do it again. Huh?
Yeah,
Let's do it again.
the last part especially.
Let's do it again. So we have the movers formula that z to the n is the same as r to the n, so cosine of n theta plus I sine of n theta. This is the formula we're using, where of course z is x plus iy. We've been given the number z as 2 exponent I pi divided by 4. Then we asked to find z squared. Okay, so in that case, n is 2. So remember, by Euler's formula, this is the same as 2 times cosine of pi divided by 4 plus I sine of pi divided by 4. Are we together up to this point?
Yes. Yes.
Good.
Yes.
Now we use the theorem z squared should be r to the n. So in this case, r is 2. What's outside the bracket? Okay. No.
Yes.
So r should be 2 squared. Then in bracket, cosine, we multiply the angle by 2. Okay. So here, if it n, you multiply the angle by n, but we have n is 2. So we multiply the angle by 2. So cosine of 2 times pi. I've multiplied pi divided by 4 times 2 plus I times the sine of 2 pi divided by 4. Of course, you can leave your answer at this stage. It's not a problem. But you can carry on the simplification if you want. 2 squared is 4, okay?
Yes.
2 squared is 4. And now what is inside? I'll advise you to use your calculator. Okay?
Mm-hmm.
Use your calculator. Compute, change the angle to radians and compute cosine of 2 pi divided by 4. Those who have a scientific calculator. Of course, 2 pi divided by 4 is the same as pi over 2. Huh? These 2's can cancel and get pi over 2. So change your calculator, scientific calculator, change the angle to radians and compute cosine of pi divided by 2. What's cosine of pi divided by 2 from the calculator? Anyone in the calculator?
0.49.
0.9999.
Yeah.
Have you changed the angle to radians? Change the angle to radians, or you can put it in Google. Cosine of pi over 2. You're supposed to get 0.
Negative 0.5.
Cosine. Cosine of
Cosine of pi over 2.
Cosine of pi over 2.
Yeah,
You're getting
negative 0.5.
negative 0.5. Really? In radians, I've said change the angle to radians, not degrees. Change the angle to
Negative
Zero.
1.
0.
Oh my God. Let me share my screen and show you what I'm talking about.
Oh, it's 0. It's 0. Sorry.
Are you convinced it is 0?
Yeah.
Yeah, it's 0.
Good, good, good. I wanted to share the screen and show you how it's done, but it's okay. So this is 0
Sure, if I didn't get it right.
plus I. How about this?
Excuse me, sir.
Yes.
I didn't get it. Could you please just share the screen and show us the way?
Yes, I can show that.
Thank you.
Good, 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 good. Share screen. That's not difficult. No, some difficult question. Calculator, this is good. Good. So, good. Is everyone seeing my screen? Hello?
Yes, we are seeing your screen.
Yes, good. So first of all, change the angle to radians. Huh? That's the first thing I've done. Then I compute cosine of pi, where is pi? This is pi divided by 2, which is pi over 2. Cosine of pi over 2.
So I think you divide first of all pi over 2, then find the cosine of the answer.
When you do it directly, you're using the degrees.
Okay, now,
instead
I
of
get,
the-
now I understand why some of you are getting the, okay. Grab that one. Let me see pi divided by 2. And then now cosine of the answer.
That is using degrees.
It's strange. No, but I put it to radians. Cosine 2.
You're supposed to put it in degrees. When you put in degrees, you'll get 0.
No, in degrees it should be 90. If you put in degrees, then you should be getting cosine. It's the same as getting cosine of 90.
No, sir, put it in degrees, then do pi divide by 2, then get the cosine. I've tried that and it has given me 0.
I'm doubting that calculator. Let me use this other one. I don't think that calculator is. So this is radians. The cosine pi divided by 2. That gives me a 0. So there's a problem there. The calculator I was using before. Then if you change this to sine of pi, where is pi? Pi divided by 2. That gives you 1. Okay. If you do it in radians, huh? But if you do it in degrees, pi over 2 is the same as 90. We said 2 pi is 360, so pi is 180. Therefore, pi divided by 2 is 90 degrees. So in degrees, I'll be computing sine of 90 degrees, which will give me, and I'll be computing cosine of 90 degrees, which will give me 0. Okay. Everyone satisfied? Hello?
Yes.
Yes. Yeah, the other calculator I was using was add some I don't know what's wrong with it. It's okay now. So what we have is that this is 1. Therefore, 4 times 0 is 0. So 4 times I gives you 4i, which is what I get there. But this simplification is not necessary. If you ask to just compute the powers, just apply the theorem and leave your answer at this stage. Okay. Another example, the same number. Let's say you want to compute z power 10. Okay, where z is 2 exponent I pi by 4. Z power 10. What does the theorem say? Raise r to n in this case, so we'll have 2 raised to 10. So you have z is 2 exponent I pi by 4. You raise 2 to power 10 and then multiply the argument by 10. So I times 10 pi divided by 4, which is the same as 2 power 10. 2 power 10. What is 2 power 10? Is it 1024? Should be 1024. And then by Euler's formula, I can write this part as cosine of 10 pi divided by 4 plus I sine of 10 pi divided by 4. You can leave your answer at that stage. You don't have to simplify. So all you're doing is taking r, raise it to n, and then multiply the angle by n. Okay? If I ask you to find z power, I don't know, maybe 60,000. Raise to 60,000. Okay? Exponent of I pi over 4, multiply this by 60,000. Okay? Is the idea home? Hello guys, talk to me. If there's a problem, you say we look at it.
Could you just go over from equals 1024?
Yeah.
Yes, from there.
This is already done. This is z to the 10. I said you can leave your answer in this one, or you want us to simplify this?
No, I can't quite read the end part after cosine at 10 pi over 4. Yeah,
this is just what I have up here. It's the same thing. It's the same thing. I have 1024 in bracket cosine 10 pi divided by 4 plus I sine of 10 pi divided by 4. It's better now?
Yes.
Raise r to 10, multiply the angle by, the angle is also called the amplitude, multiply it by 10. If I give you, raise it to power 100,000, raise the radius to 100,000, multiply the angle by 100,000. Okay? It's as simple as such.
So I have a question.
Yes, go ahead.
In the last class, there was an example you gave that I raised to power 27.
Yes.
And then you said I raised to power 26 plus 1, and then
Good.
Explain that.
By the way, were you guys able to do the homework I gave you? You were to multiply some numbers and you were to divide some complex numbers.
You did?
Yes.
Did you do that homework?
No. Yes, I did.
What did you get? You should have sent me so that I have a look.
Okay, I'll send mine after the class.
Of course, it's not going to be graded, but it's just to, for you to understand these things more, okay? this class should not just be about, getting A's and passing your exam, It's about understanding these concepts, okay? My aim is that you understand. Don't worry about the grade or the marks or whatever. My main objective is that you understand what you're doing. That if you're talking of complex numbers, you know the absolute value of a complex number, you know the magnitude of a complex number, you know how to find, rectangular representation, trigonometric representation, polar representation, exponential representation. You can compute the powers using the Moivre's theorem. You can find roots, which you will see later. You can multiply two complex numbers comfortably. You can divide them. You can add, subtract. Okay. So those who did, please send your solution so that I can have a look. So I gave you I to the 27. Was that, did I get it right, Abdi Hakim?
Yes, I to 27.
So the only thing you need to remember is that I squared is -1. This has become like a song now. I squared is -1 because we defined I as the square root of -1. So 27, there are so many ways of decomposing this. We need the laws of exponents. You remember when you're doing exponents, integer exponents and roots, there's this for adding exponents, then there was raising a power to another power, and then there was for division. To deal with problems like this, remember that I squared is -1 from its definition. This is the definition, so when you square both sides, this side is I squared, the other side, the square will remove the root symbol and you get what is inside. And then you need this law that if you're multiplying two, exponents with the same base, just add the exponents and maintain the base. If you're having an exponent raised to another exponent, maintain the base and then multiply the exponents. And then if you're dividing, simply subtract the exponents. This is all you need to deal with problems like this. Once you know this, I can even ask you to compute I power, 20,000 or 26,000 or a billion or a million or a trillion. So let's see how you compute I to the 27. You can write I to the 27 as I to the 26 plus 1, because 27 is the same as 26 plus 1. True or true?
True.
27 is the same as 26 plus 1. So I can write this I to the 27 as I to the 26 plus 1. Okay? Now, look at this rule. A to the m times A to the n is the same as A to the m plus n. Now I'm on the right-hand side, I want to go back. So I have I to the 26 plus 1. I can write this as I to the 26 multiplied by I to the 1. Using this first rule. Are we good?
Yes.
Okay. Of course, any number raised to 1 simply stays the same. If you raise 10 to the power 1, it is 10. 20 to the power 1 is 20. Okay? I to the 26. I can again write 26 as 13 times 2. So I to the 26, I can write this as I squared 13 times I. Where here I've done times I because I to the 1 is simply I. And now here I've used the second law.
Your handwriting cannot be seen. What did you write there?
What I wrote here.
Yeah.
I squared all things raised to power 13 times I. Where the 26 that we have is 2 times 13. I'm using the second law now. Raising an exponent to another exponent is like multiplying the exponents. So I have 26 as a product of 2 and 13. Therefore, I can write I to the 26 as I squared raised to 13. Are you good up to that point?
Yeah.
Yes.
Or should we repeat again? And then we know that I squared is minus 1. So this I squared that we have inside here is simply minus 1. So this is simply minus 1 raised to power 13 times I, where the minus 1 is I squared that we have inside. I'm looking for what I know. I know that I squared is minus 1. So this I squared is minus 1. Now, what is minus 1 power 13? What is negative 1 raised to 13?
Minus 1.
Negative 1.
Negative 1.
Negative 1. So this is simply negative 1 times I, which gives you negative I. Let me give you another example. Maybe it will sink in. Let's say you want to compute I power 4. So let's do it in order. Let's compute the first few powers. Let's compute I cubed. I to the 4, I to the 10. Then lastly, you guys will compute me I to the 2000. This is for you. I cubed. You can write I cubed as I to the 2 plus 1 using this first rule, because 2 plus 1 is 3. And I'm sure you all agree with me. Then using this rule, you can split a to the m plus n as a to the m times n. So I can split this as I squared times I power 1. But what is I squared? Negative 1. So this is going to be negative I. How about I to the 4? We can write I to the 4 as I to the 2 times 2. Someone can also write it as I to the, use this space. I just want to show you that there is no unique way of dealing with such problems. You can use any form that you want, so as long as you obey the rules. Someone can also write I to the 4 as I to the 2 plus 2. Okay? 2 times 2 is 4, 2 plus 2 is 4. So either way, you're fine. If you write it as I to the 2 times, we know this is the same as I squared squared, because of the law of raising an exponent to another exponent. So this is the same as I squared squared, but we know I squared is negative 1. So this is like negative 1 squared, which will give you 1. If someone writes 4 as 2 plus 2 instead of 2 times 2, then they will have I raised to 2 times I raised to 2. But I raised to 2 is negative 1. So negative 1 times negative 1, which gives you 1. So either way, you'll always get the same answer. Or because I know I cubed, I can write I to the 4 as I cubed. I can write this as I to the 3 plus 1, which is the same as I cubed times I to the 1. But I know that I cubed is negative I. So this will be negative I times I. And what is negative I times I? Of course, this is negative 1 times I squared. But I know I squared is negative 1. So this is negative 1 times negative 1, which gives me 1. There is no standard way of doing this. It's just how what works for you. As long as you obey the rules of adding the exponents, subtracting the exponents, multiplying the exponents where applicable, and also the definition of I, that I is the square root of -1. So if you square it, you get -1. By the same analogy, can someone give us I power 10? What's I power 10?
The answer.
Sorry?
The time.
The time.
It's time.
-1.
Okay, we will look at this next time. Go and do this as homework for today. Compute I to the 10 and I to the 2000. We'll start from there next time.
Just a minute.
Today, there's someone who came 10 minutes late and then made us do what we had done before. And then now you're saying time is up. So next time, make sure you come on time, okay? Try to keep time.
Okay, sir. You quite interesting.
Professor.
Yes, sir. How are you?
Fine. I was asking if you already took the attendance.